Look at this equation. It's pretty dense, right? Mysterious even. But for many people, it's actually profoundly elegant.
Hmm.
This is Schrödinger's equation. It's really the mathematical cornerstone of quantum mechanics.
It absolutely is.
And it's not just some abstract formula. Think of it like a living map of the quantum world. It shows us how particles evolve, how they interact, and maybe the most striking thing, how probabilities actually shape the fabric of reality.
Yeah, without it, our whole picture of the universe at that tiny scale just falls apart.
Exactly. Now, what if we could actually harness this equation, not just to understand things, but to build with it,
Right.
to create machines that really do think in probabilities, machines that kind of mirror the deep complexity of reality itself?
That's the core idea, yeah.
Well, that's basically quantum computers. They aren't just faster tools. They're more like a window into the universe's fundamental operating system.
But a completely different approach.
Yeah. So our mission in this deep dive is to unpack what quantum computing really is. We want to show you its amazing capabilities, but also its really crucial limitations, and why it's so much more than just a souped-up supercomputer.
Yeah, there's a lot of hype, but also real substance.
Definitely. You're going to walk away from this feeling genuinely well-informed. So, okay, we're talking about machines based on quantum mechanics. What was that first big conceptual jump, the spark that made researchers think, hey, maybe we could actually build something like this?
Well, it really did start out sounding like science fiction to a lot of people.
Mhm.
Back in 1980, a physicist named Paul Benioff, he sort of laid the groundwork.
Okay.
He came up with this idea of a quantum Turing machine. So instead of the simple on or off of classical bits, zeros and ones,
Right.
his idea involved qubits, these tiny units that could follow well, the very strange rules of quantum mechanics.
Which are pretty counterintuitive.
Extremely. And at the time, you have to remember, classical computers, even though they were getting faster, were hitting this fundamental wall.
A wall.
Yeah.
In what sense?
They just couldn't simulate quantum systems properly
Yeah.
because the complexity, it grows exponentially.
Ah, okay.
So trying to model even a fairly simple molecule on a classical supercomputer, it quickly needed more computing power than, like, the whole planet had.
Wow. Okay.
And this challenge, this very real problem, it caught the attention of some brilliant minds, people
Yeah.
like Yuri Manin and famously Richard Feynman.
Right. Feynman.
Yeah, and they independently came up with this really radical idea. To truly understand quantum systems,
Yeah.
maybe we needed computers that worked like them, that actually used those same quantum effects.
So you use quantum mechanics to compute quantum mechanics.
Exactly. Fight fire with fire, so to speak.
And it wasn't actually that long before these sort of theoretical ideas started finding surprising applications, even practical ones like in cryptography.
Precisely. Yeah, building on those early thoughts, in 1984, Charles Henry Bennett and Gilles Broussard had this major breakthrough. They applied quantum principles to create something called quantum key distribution, or QKD.
Hmm.
And the promise was fundamentally unbreakable communication.
Unbreakable. How does that work?
So here's the key difference. Classical encryption, it relies on math problems being really hard to solve, right? But a powerful enough computer could eventually crack them.
Theoretically, yeah.
QKD, though, its security isn't based on math hardness. It's based on the actual laws of physics, immutable laws.
Okay, like what?
Imagine Albert wants to send a secret key to Catherine. They'd do it using individual photons
Yeah.
encoded in specific quantum states.
Okay, single particles of light.
Right. And the weird thing about quantum mechanics is, if anyone, let's call her Ella, the eavesdropper tries to observe or copy those photons.
Mm-hmm.
The very act of observing changes their state. It's unavoidable.
Ah, so Ella listening in actually messes things up.
Exactly. She leaves behind this undeniable trace, like footprints in the snow.
Oh,
So Albert and Catherine, they publicly compare notes on a small sample of the photons if they see discrepancies caused by Ella.
They know someone was listening.
Yep. They just discard that key and start over, generate a new one. This makes sure only they have the final secure key.
And even a future quantum computer couldn't break this.
Nope. Because it's not a computational puzzle to solve. It's a physical fact. You can't observe without disturbing. That's just how quantum mechanics works.
That's incredible. Is this actually being used now?
Oh, yes. It's not just theory anymore. QKD is being deployed today. You see it in really sensitive areas, government communications, financial systems, anywhere that needs absolute secrecy.
Fascinating. Now, when we talk about quantum computers, sometimes you hear people almost dismiss classical computers, like they're suddenly lame.
Yeah, that's definitely not the right way to look at it.
No, right. It's crucial to remember classical computers are far from obsolete. I mean, without them, we wouldn't have, well, anything digital. The internet, sending people to the moon, all that runs on their precise, reliable power.
Absolutely critical point. They are amazing machines, just
Yeah.
different.
They just have their limits.
Exactly. Classical computers work with bits, and a bit is always either a 0 or a 1, a definite state.
Like a light switch, on or off.
Perfect analogy. Think of flipping a whole series of tiny light switches on or off in a very specific order. That's how they process information.
So, weather prediction systems, for example.
Yeah, they take huge amounts of data, temperature, pressure, humidity, wind, and break it all down into millions, billions of these binary switches. Or your digital photos, millions of pixels, each represented by bits.
Okay.
And they're incredibly fast at these kinds of tasks. But the key is they solve problems one possibility at a time, step by step.
Sequentially.
Right. And that makes them painfully slow, sometimes completely impractical, for problems where the number of possibilities just explodes, like simulating complex molecules or certain optimization puzzles, or, as we mentioned, cracking some types of modern encryption.
Okay, so this is where it gets really interesting. This is the fundamental shift. Quantum computers play a completely different game using these qubits. What makes their approach so revolutionary?
It really comes down to two core quantum principles. The first one is superposition.
Okay, superposition.
So, unlike that classical bit, either 0 or 1, a qubit can be a 0, a 1, or, crucially, any combination of both at the same time.
Both, simultaneously.
Simultaneously. Think of it like this. If you're trying to guess a 4-digit PN, a classical computer tests 0000, then 0001, then 0002, one after another.
All right, sequentially.
A quantum computer, because of superposition, could, in a sense, explore all 10,000 combinations at the same instant.
Wow, so it's not that each calculation is faster.
No, not necessarily. It's about exploring this vast space of possibilities in parallel,
Oh,
all at once.
okay, that's superposition. What's the second principle?
The second one is entanglement. This is maybe even weirder.
Oh, great.
Yeah, this is where qubits become linked, intrinsically connected. So the state of one qubit instantly influences the state of another, no matter how far apart they are.
That's the spooky action at a distance thing Einstein talked about.
That's the one. It allows for this kind of synchronized collective processing power. Imagine you have a team of genius problem solvers.
Okay.
But with entanglement, they can instantly share and integrate their insights with each other. No delay. They work together seamlessly on problems that would take a classical computer, well, maybe millions of years.
That connection allows for faster problem solving somehow.
It allows them to correlate their information in ways classical bits just can't. And the scale here, this is what's truly mind-boggling.
Go on.
With just 300 entangled qubits, just 300, a quantum computer can represent more states simultaneously than there are particles in the entire observable universe.
Wait, say that again. More states than particles.
Than every atom, every star, every galaxy combined.
That's hard to even grasp.
It really is. So it's not just about speed in the traditional sense. It's about the capacity to hold and process an unbelievable amount of information simultaneously, exploring possibilities on a cosmic scale.
Okay, so if we connect these incredible capabilities, superposition and entanglement, to actual real-world impact, where do quantum computers genuinely shine? Where can they make a difference?
Well, one of the biggest areas, and maybe one of the earliest drivers, is simulating chemical reactions, molecules.
Right, you mentioned classical computers hit a wall there.
They hit an exponential wall, a molecule with just, say, a few dozen atoms. Trying to accurately model its quantum behavior classically might need more computing power than exists in the whole world.
So it's basically impossible.
Pretty much. But quantum computers, because they operate on quantum principles, they can handle this complexity much more naturally, with relative ease, potentially.
And the impact of that could be huge.
Oh, enormous. Think about drug discovery, designing molecules that interact perfectly with targets in the body, or material science creating new materials with specific properties, like better catalysts or superconductors, even just understanding the basic building blocks of life.
Okay, so chemistry and materials. What else?
Then there's cryptography, which we touched on with QKD, but from the other side, breaking codes.
Ah, the code-breaking potential.
Exactly. Current internet encryption, like the common RSA algorithm, its security relies on one thing. It's incredibly difficult for classical computers to take a very large number and find the two prime numbers that multiply together to make it.
Factoring large numbers.
Right. It can take even the biggest supercomputers millions of years for the kinds of keys used today. There was an RSA key, RSA 768, that took the equivalent of 2,000 years of standard computing time to crack back in 2009.
Wow.
But then comes Shor's algorithm. It's a quantum algorithm designed specifically for quantum computers.
And it can factor large number.
Efficiently. It uses superposition and other quantum tricks to find the factors much, much faster than any known classical method. It basically turns that impossible problem into a manageable one.
So that's a major threat to current security.
It's a huge wake-up call for cybersecurity, absolutely.
Yeah.
We need to move towards quantum-resistant encryption methods.
Okay, and you mentioned optimization.
Yes, optimization problems. These are everywhere. Think about finding the most efficient routes for a fleet of delivery trucks.
The traveling salesman problem, kind of?
Exactly, but on a massive scale. Or scheduling airline flights to minimize delays and costs. Or managing traffic flow in a big city.
Things with tons of variables and possibilities.
Tons. Classical computers can try to find good solutions, make educated guesses, use heuristics. But finding the absolute best, the optimal solution, that's often computationally impossible for them.
And quantum computers.
Because they can explore all the possibilities simultaneously using superposition and entanglement, they could potentially identify the truly optimal solution in seconds or minutes.
Which would mean?
Massive efficiency gains, saving huge amounts of energy, time, resources. It's not just convenience. It's about fundamentally changing how we manage complex systems.
That really does paint a picture of incredible power. It sounds almost like a magic wand for solving these really tough problems. But I'm guessing there's a big but coming. A crucial caveat. These aren't some universal fix for everything, are they?
You are absolutely right. That's a critical reality check. They are not a universal solution, not even close.
Okay. So where do they fall short?
Well, first off, for loads of everyday tasks, quantum computers are, frankly, useless.
Useless? Like what?
They're completely impractical for what we call deterministic problems. Tasks where every step is clearly defined, predictable. Checking your email, streaming a video, running the physics in a video game.
Stuff our regular computers do just fine.
Exactly. Classical computers are perfect for those. They execute instructions sequentially, quickly, efficiently. Using a quantum computer for checking email, it'd be like using a spaceship to drive to the grocery store.
Right. Total overkill and probably wouldn't even work well.
It'd be painfully impractical.
Yeah.
And even when they are suited for a problem, there are major challenges.
Okay, like...
Remember, superposition means exploring all possibilities. Well, when you finally measure the result, the quantum state collapses. It gives you just one of the many possible outcomes based on probability.
So you don't get the all possibilities answer directly.
No, you often have to run the computation multiple times, gather statistics to get a reliable answer. It requires really clever algorithm design to actually extract useful information from that probabilistic outcome.
Okay, so they're probabilistic, not definite. What else?
Then there's the sheer fragility of the qubits themselves. They are incredibly sensitive to heat, to vibrations, to tiny bits of electromagnetic interference. Anything from the outside world can knock them out of their delicate quantum state.
So they need special conditions.
Extreme conditions. Often temperatures near absolute zero, colder than deep space. Plus, near-perfect isolation from any kind of noise.
That sounds expensive.
Incredibly expensive and resource-intensive just to maintain the environment they need to operate.
And if they're so fragile, errors must happen.
All the time. Errors are frequent. And correcting these quantum errors, that's another huge challenge. It's not simple.
How do you correct them?
It often requires using many, many additional physical qubits just to act as backups and perform the error correction for a smaller number of logical qubits that actually do the calculation.
So you need way more qubits than the problem itself seems to require.
Exactly. A problem that might theoretically need, say, 1,000 perfect logical qubits could actually require millions of physical qubits to achieve robust, fault-tolerant computation.
Millions? Where are we now with qubit counts?
We are far, far away from that.
Yeah.
Most quantum computers today are prototypes. They might have a few dozen qubits, maybe 100 or so in some cases.
Can you give examples?
Sure. Google's Sycamore platform, which made headlines a few years ago, that's largely used for specific research like in cryptography. Rigetti has machines like Aspen M3, focused more on things like quantum chemistry or machine learning applications.
But we're talking dozens, not millions.
Right. For widespread practical applications tackling those really big problems, we need thousands, ideally millions, of stable, error-corrected qubits. We're just not there yet. It's a massive engineering hurdle.
Okay. So fragile, error-prone, need extreme conditions, hard to scale.
Hmm.
Any other limitations?
Just to reiterate, they are highly specialized machines. They excel at specific types of problems, the ones we've discussed, like simulation, factoring, certain optimizations. They are not general-purpose computers.
Right.
For the vast majority of tasks that keep our modern world running, from word processing to managing databases to browsing, the web classical computers are still, and likely will remain, the best tool for the job.
So summing that up, it's clear quantum computers won't replace classical ones. That's not the goal.
Not at all.
They're going to complement them. They'll tackle these extraordinary challenges that are just fundamentally beyond the reach of classical systems. Tools for the extraordinary, not the everyday.
Precisely. Think of them as a powerful new type of processor for specific, incredibly hard tasks.
Okay. Now, speaking of advanced technologies tackling complex problems, how does quantum computing intersect with another field that's just dominating headlines constantly? Artificial intelligence, AI.
Yeah, the intersection of AI and quantum is fascinating, and it's evolving quickly.
How do their strengths compare?
Well, AI's great strength, especially modern machine learning, is its ability to learn patterns from enormous data sets and solve complex problems based on that learning. Think about DeepMind's AlphaFold.
Right, figuring out how proteins fold.
Exactly, a problem that stumped scientists for decades.
Yep.
AI figured it out by learning from data. AI is fast, it's adaptable, it's surprisingly good at tasks we once thought only humans could do, or were just computationally intractable.
Okay, that's AI's strength. Learning from data, pattern recognition.
Right. Now contrast that with quantum computing's unique power, what we call the quantum advantage. Its ability to tackle problems that classical computers, even supercomputers running AI, simply cannot handle at all.
Because of superposition and entanglement?
Exactly. For problems that involve exploring these immense possibility spaces, like simulating quantum systems or factoring.
So they seem quite different in their core strengths.
They are, but here's where it gets interesting. There's an overlap starting to emerge. AI has actually begun to sort of encroach on territory that some people thought might be exclusively quantum.
How so?
By training AI models on massive data sets, sometimes incorporating known physics rules into the AI training, researchers are finding that AI can sometimes achieve similar results for certain scientific problems without needing actual quantum hardware.
So AI is getting good enough to simulate some complex things too.
In some cases, yes. Demis Hassabis, the CEO of Google DeepMind, he's even suggested that advanced AI might end up solving some problems we currently think we'll need quantum computers for.
Which could limit where quantum computers are actually needed in practice.
It potentially could, yeah. It shifts the landscape a bit. The real story, though, probably isn't about one replacing the other.
More about synergy.
Exactly. It's about understanding where each technology truly excels and how they might work together. They're both pushing boundaries, they're complementary, and together they're really reshaping how we approach problem solving across so many fields.
Okay, complementarity. That makes sense. Now let's shift gears to something truly mind-bending, an application that sounds straight out of science fiction.
Oh, where are we going now?
Wormholes. In late 2022, physicists actually made headlines simulating wormhole-like behavior. They used Google's Sycamore quantum processor.
Yes, that experiment.
Now, we need to be super clear here. They did not create a physical wormhole, right?
Yeah.
No tunnel through space-time.
Absolutely not. Let's get that straight up front. No physical wormhole was made.
But the experiment gave some kind of insight into how information might behave if it could traverse a theoretical wormhole. What was that actually about?
Yeah, it was a really groundbreaking experiment because it tried to bridge concepts from quantum mechanics and general relativity, two areas of physics that are notoriously hard to connect.
The very small and the very large.
Precisely. The experiment focused on quantum entanglement and something called quantum teleportation, transferring quantum information. What the researchers did was implement a highly simplified model on the Sycamore chip.
A model of what?
A model based on something called the holographic principle.
Okay, the holographic principle sounds complicated.
It is, but the basic idea is fascinating. It suggests that our complex 3D plus time universe might be mathematically described as a projection from a simpler, lower-dimensional quantum system, like a hologram stores a 3D image on a 2D surface.
Wow. Okay, so the universe as a hologram.
In a mathematical sense, potentially. So, using this principle, they designed a quantum circuit that mimics some expected properties of information traveling through a type of theoretical wormhole known as an Einstein-Rosen bridge.
And what did they see?
By encoding quantum states and manipulating them on the chip, they observed information traversing the simulated wormhole in a way that matched theoretical predictions based on quantum gravity ideas. It showed that, yes, quantum computers could be tools to actually probe these really deep questions about gravity and quantum mechanics.
So it's a simulation, but one that tests fundamental physics ideas.
Exactly. And it connects to an even bigger, more profound idea.
Which is?
The idea that the universe itself might actually be a massive quantum computer.
The whole universe.
Think about it. The fundamental rules of quantum mechanics, superposition, entanglement, interference, they don't just describe how our quantum computers work. They seem to describe how the universe itself operates at its deepest level.
So the universe is running calculations.
The physicist Seth Lloyd famously proposed this. He suggested that every interaction between particles everywhere in the cosmos could be seen as a fundamental computation, the universe constantly computing its own future state.
So this perspective, it's not just a cool metaphor. It genuinely reframes how we think about the cosmos. It suggests understanding quantum computing could actually unlock the, I don't know, the deeper logic behind existence.
That's the profound implication,
Yeah.
yes. If the universe is fundamentally computational, and specifically quantum computational,
Then the implications are huge.
staggering. Imagine if we could build quantum computers powerful enough. Simulating wormholes is just a tiny first step. We could potentially model black holes accurately, understand dark matter, maybe even simulate the conditions right after the Big Bang.
Asking questions we couldn't even properly frame before.
Exactly. Providing tools to answer questions that have puzzled scientists for centuries. What's compelling is how natural it feels in some ways. The math that governs quantum computers seems to be the same language the universe speaks.
Like reality was sort of designed to be understood this way.
It feels like that sometimes. Every breakthrough we make in building these machines potentially brings us closer not just to solving problems, but to understanding the fundamental nature of reality itself.
Okay, let's try a thought experiment to really drive home the sheer complexity we're dealing with here. The kind of complexity that both classical and quantum computers are trying to grapple with. Imagine just flipping a coin,
Okay, simple coin flip.
but you flip it 266 times.
Okay, 266 flips. That sounds manageable, but it's really, really not.
How many possible sequences of heads and tails are there?
It's 2 to the power of 266.
Which is a big number.
It's an absolute astronomical number. To give you a sense of scale, 22 in HC66 is larger than most estimates for the number of atoms in the entire observable universe.
More sequences than atoms.
By a lot. It's mind-boggling. Try to imagine counting them all, even if you had, say, 10 billion universes.
Okay.
And each one had 10 billion galaxies, and each galaxy had 10 billion planets, each with 10 billion people.
That's a lot of people counting.
And each person had a super powerful computer counting 10 billion sequences per second. It would still take about 100 times the current age of all those universes combined just to list every single possible sequence from those 266 coin flips.
Okay, that's impossible to comprehend, basically. So what's the point here?
The point is, this illustrates something fundamental about us and the universe. We humans, our brains, we're inherently drawn to simplicity.
We look for simple patterns, simple explanations.
Exactly. We build models, theories that explain things in the simplest possible terms because that's what we can process. There's that old analogy, right, about the person looking for their lost keys at night.
Not where they dropped them, but under the street lamp.
Yeah, just because that's where the light is. We tend to focus on the simple, the manageable parts of reality because that's what we can easily see or compute.
But reality isn't always simple.
Usually it's not. The simple stuff is often the exception. Think about the coin toss again. If each flip is truly random and independent, okay, we can handle the probabilities. That's manageable.
Right, 50-50 each time.
But what if, in some complex system, the outcome of each flip depended intricately on all the ones that came before it in some totally unpredictable, non-linear way?
That sounds more like real life.
That's the uncountable complexity. Life, biology, weather, economies. They're usually messy and complicated, unless we deliberately filter them or stick to the really easy parts.
And how does this relate back to computers?
Well, classical computers, fundamentally they produce sequences of bits, like those coin flips. But they have to stick to simpler patterns, predictable sequences, or they just crash.
They can't handle true, deep complexity.
They struggle immensely. They have to simplify. Your computer will never just randomly generate every possible sequence of bits. It follows instructions. It sticks to the patterns we program into it. That's why modeling really complex systems, like the full chaos of weather or the emergent behavior of a living cell, is still so incredibly hard for them. They're only as smart as the simplicity we force them into.
And quantum computers, even though they tap into quantum complexity, they're also tools we design for specific problems. Problems we think are solvable with the resources we have.
Exactly. We're still directing them, focusing them on problems, structured in a way we think they can tackle.
Yeah.
The universe's underlying complexity isn't really an obstacle we can just remove. It's just a fact.
Right.
Our technology, whether classical or quantum, helps us manage that complexity. It gives us tools to explore bits of it in controlled ways, but it doesn't eliminate the fundamental vastness and intricacy out there.
Wow. Okay, we have covered an incredible amount of ground today. We've gone from the foundational equations of quantum mechanics, like Schrodinger's, all the way to simulating bits of the cosmos. It really underscores how quantum computers represent this entirely new frontier in human understanding.
Absolutely. And I think it's important to remember that every step forward, every breakthrough in building and controlling these quantum systems, it doesn't just bring us closer to solving practical problems like drug discovery or optimization.
Right.
It also brings us closer, potentially, to understanding the very nature of reality itself, what it's made of, how it works at the deepest level.
Which leads to a final, pretty provocative thought to leave everyone with. If our universe, as some theories suggest, truly operates like a vast quantum computer, and here we are just starting to build our own small versions of these machines, what does that really imply about the line between, say, simulation and reality?
It does make you wonder.
Could our deep dives into quantum mechanics, into building these computers, ultimately reveal whether the fundamental rules of our own existence are, in fact, computational?
Yeah.
And if they are, what on earth does that mean for our future?